Remember student now? Now I am going to writing now general formula for half-life time of nth order reaction. Now general representation giving now for half-life time. Directly I am giving for nth order reaction. For nth order reaction T of is equal to what? 2 to the power of n minus 1 divided by n minus 1 into Kn C naught power n minus 1. Generally what? This half-life time is depend on initial concentration of the reactant. For zero order reaction n is equal to 0, therefore half-life time independent on initial concentration of the reactant. Remember student, for suppose for zero order reaction, for zero order reaction, for zero order mean n is equal to what? 0 taken out here, n is equal to 0 substitute here, T of directly proportional to 1 by C naught power 0 minus 1, or T of is directly proportional to 1 by what C naught power minus 1. C naught power minus 1 mean 1 by C naught, therefore T of directly proportional to C naught. This is valid only for zero order reaction. So for zero order reaction, half-life time is directly proportional to what? Initial concentration of the reactant. Now according to I am writing what? For nth order reaction, directly I am taking nth order here. For suppose I want to find out zero order, n replacing 0. For suppose I want to find out now first order reaction, n value replacing 1. Now similarly I am find outing what? T of first order reaction. T of first order reaction. T of first order reaction. First order what reaction? T of first order reaction. T of is directly proportional to 1 by C naught power what? Here n minus 1 given. First order reaction what? T of is directly 1 by C naught power 1 minus 1, 0 power 0 value 1. Therefore, that is why T of is independent what on initial concentration of the reactant. It is valid only for first order reaction, because n value 1 substituting here. T of is directly proportional to 1 by C naught power 1 minus 1. Therefore, T of is directly proportional 1 by C naught power 1 0 value 1 here. That is why half-life of first order reaction is independent on initial concentration of the reactant. So, half-life of first order reaction half-life of first order reaction independent on initial concentration of reaction. Initial concentration of reactant. That is why I derived already for first order reaction T of value given 0.693 divided by K given. Once you see here, last class given already, T of is equal 0.693 divided by K. This is value only for first order reaction. See, next concept I am going to be discussing, that is called integrated rate equation of first order gaseous phase reaction. integrated rate equation for first order gas phase reaction. Integrated rate equation of for first order gaseous phase reaction. Now I am considering, now I am taking what one first order gaseous phase reaction. Consider first order gaseous phase reaction. First order gas phase reaction. Consider first order gaseous phase reaction, that is A gas gives rise to B gas plus C gas taken now. Now I am finding what integrated rate equation in gaseous phase reaction. It means what? In terms of partial pressure I am going to find out now here. Now at T is equal 0 time, the initial concentration of the initial partial pressure of the reactant value P naught value take now. Initially partial pressure of the reactant value P naught at T is equal 0 time, there is no product, that is why 0 0 take now. Now at T is equal to T, at equilibrium I am observing direct, at equilibrium some partial pressure of the reactant is dissociating, that is X. See P naught minus X taking, X amount what? X partial pressure dissociating into what? Product side. Now I am studying what here? Stoichiometric coefficient. Here stoichiometric coefficient 1 1 1 is there. Now 1 mole giving 1 mole, therefore X mole giving X. Here 1 mole giving 1, X mole giving what? X mole here. Where X is nothing but what? Amount, dissociating amount of partial pressure of the reactant. X is nothing but at equilibrium what? Remaining value P naught minus X, this is what? Remaining value at T is equal T time, remaining partial pressure of the reactant. At T is equal 0 time what? Initial partial pressure of the reactant value is P naught. At T is equal T time, remaining value what? P naught minus X. Now total pressure at equilibrium I am find out. Total pressure at equilibrium. Now total pressure find out. Total pressure at equilibrium. At equilibrium I am find out. Total pressure at equilibrium. P total equal to P naught minus X plus X plus X. 1 plus X minus X will get cancelled. Therefore, PT is equal to P naught plus X. I want to find out in X value. X is equal to P total minus P naught. Whatever X value is coming here, that X value substituting in this equation. Therefore, at T is equal to 0 time, what? The initial partial pressure of reactant is P naught. At T is equal to T time, the remaining concentration, remaining partial pressure of the reactant value P naught minus X. This X value substituting here, what? P naught minus X value PT minus P naught. Finally what? Finally minus into minus plus here, finally this value will get 2 P naught minus P total. Mean P naught is a initial partial pressure of the reactant at T is equal 0 time. At T is equal to T time, remaining partial pressure of the reactant value 2 P naught minus PT. We are already computed what? At T is equal 0 time, the initial concentration of the reactant value C naught taken. What? At T is equal T time, what? The remaining concentration of the reactant value Ct taken, that is in terms of what? Concentration I am taken. Now I am taking what? In terms of partial pressure, initial partial pressure of the reactant P naught taken now. After T time, the remaining partial pressure of the reactant value 2 P naught minus Pt. Generally, partial pressure is directly proportional to concentration. Now, in terms of concentration in first order reaction, I am replacing what with partial pressure, because according to what ideal gas equation, for gaseous equation, you know, PV is equal to nRT. PV is equal to nRT, P is equal to N by V into RT. P is equal to N by V mean concentration, P is equal to CRT. Therefore, partial pressure is directly proportional to concentration. Now, concentration term replacing what partial pressure. Now, according to first order reaction, you know, in terms of concentration already I given what K is equal formula given 2.303 divided by T log base 10 C naught minus Ct given. But now I am replacing what? Concentration terms are replacing what with the partial pressure. C naught is nothing but initial concentration of the reactant at T is equal to 0 time. Ct is nothing but what final concentration of the reactant at T is equal to T time. Now, C naught value replacing P naught value initial partial pressure, Ct value replacing what? Partial pressure of what reactant after T time, that is 2 P naught minus P total. Therefore, finally we will get what integrated rate equation of first order reaction for gaseous phase reaction, that is K is equal to 2.303 divided by T log base 10 what here P naught divided by here Ct value replacing what 2 P naught minus P total. This value you have to remember is a very important formula. Many time question given in NEET level, you have to remember P naught is nothing but initial concentration of the reactant, Pt is nothing but not initial concentration, partial pressure of the reactant at T is equal to 0 time. Here P naught indicates what? Partial pressure of reactant, at T is equal to 0 time. Now Pt indicates partial pressure of reactant partial pressure of the reactant at T is equal to T time. At T is equal to T time. Remember students here, P naught indicates what? Partial pressure of reactant at T is equal to 0 time. Partial pressure of the reactant, Pt indicate partial pressure of reactant at T is equal to T time, or P total value, that one, P total value. So, this is indicates what? Integrated rate equation for first order reaction in gaseous phase reaction, in gaseous phase. See, after understanding what? Integrated rate equation of first order reaction for gaseous phase reaction, let us discuss about one more concept, that is called collision theory. Collision theory. Collision theory explain formation of product. It explain formation of product from reactant. Formation of product from reactant. Generally, collision theory explain what? Formation of product. See, generally how products are forming, generally what? In any chemical reaction, reactants are collide to each other to form products. Generally what? Product formation is take place when reactant molecules are collide to each other what then product formation is take place according to collision theory. What I am telling now, first point, what reactant molecules, reactants are collide to each other. Reactant molecules are collide to each other to form product. To form product. Generally what? Reactant molecule, for example, A is one reactant, B is one reactant. A reactant and B reactants are collide to each other to form product. But all collision do not lead the formation of product. Remember student here? First point, according to collision theory, generally what? Reactant molecules are collide to each other to form products. But all collision second point, what I am telling now here, according to collision theory, all collision do not lead formation of product. Formation of product. All collision do not lead formation of product, only effective collisions leads to formation of products, leads to formation of product. Leads to formation of product, only effective collision. That reactant molecule is called activated molecule. What are activated molecule? Only effective molecule. Effective molecules are leads to the formation of product. Those reactant molecules are called, those reactant molecules are called activated molecule. Activated molecules. Remember students here, all collision do not lead the formation of product. I am telling, all collision do not lead the formation of product. Only some collisions are leads to the formation of product. That collisions having molecules are called activated molecules. Activated molecule. Remember students here. Third point I am discussing, reactant molecule. Reactant molecule must have minimum energy. Reactant molecule must have minimum energy to form product. Called threshold energy. Threshold energy. Remember student here, reactant molecule must have minimum energy. Minimum energy hona beta for reactant molecule, then they will convert it into product, otherwise there is no product formation. I am telling, whatever minimum energy having that reactant molecule, that energy is called threshold energy, also called energy barrier, ET or energy barrier. Energy barrier. Fourth point I am explaining, according to collision theory, remember, the energy giving to reactant molecules, it converted to ET energy, then the reactants are converted to product. That energy giving to reactant molecule, that energy is called what here? Activation energy. What are activation energy? Why activation energy giving for reactant molecule? Some reactant molecule not having what ET energy, but they are not converted into product side. That's why now externally energy is applying for reactant molecule. The energy giving to reactant molecule crossing what energy barrier to convert it to product. Whatever energy giving for reactant molecule, for example, one reactant molecule here is there. For suppose it is ET energy I am telling in now. How this reactant molecule convert it to product? Convert it to product, definitely what? This reactant molecule not having what ET energy, some energy giving to, external energy giving to reactant molecule, it is crossing energy barrier, that is ET energy, then converted to product. Whatever energy giving to this reactant molecule, this energy is called what here? Activation energy. Activation energy always positive value because of energy giving here, energy giving to reactant molecule, it crossing to ET energy, definitely what? Reactant molecule must have minimum energy given, then converted to product. Definitely this much energy wanna beta for reactant molecule, then converted to product side, otherwise there is no product formation will be take place. Whatever energy giving to reactant molecule crossing ET energy barrier to convert it to product, this energy is called what? Activation energy. Now I am giving definition, write down what is activation energy giving now here. The external energy giving to reactant molecule external energy giving to reactant molecule external energy giving to reactant molecule crossing energy barrier to convert product called activation energy, that is EA. That is EA is called activation energy. For suppose one graph I am observing now, energy versus reaction progress for exothermic as well as for endothermic reaction I am observing. Now I am making one graph in between energy versus reaction coordinates, energy versus what? Reaction progress. Now here energy barrier, that is ET energy taking, this is ET. Every reactant molecule must have ET energy, then converted to product. For suppose I am taking now reactant molecule here, reactant energy, for example A comma B are reactant, reactant energy I am taking for suppose ER. This reactants converted to what? This reactant molecule what? Crossing what? Energy barrier. How this reactant molecule crossing energy barrier, it giving some energy to reactant molecule, it crossing ET energy, then converted to product, because of after formation of product the energy of product value decrease, that's why product value down writing now. Now reactants crossing ET energy converted to product. Now for reactant molecule, now some energy is giving for reactant molecule, this is what? EA, activation energy for forward reaction. For forward reaction ka EAF activation energy applying. This A plus B molecule converted to what? Here products, this is product I am writing, products, product energy I am EP taking now. Energy of product is EP, because of energy of product is less, because of after formation of product the energy of what compound is decrease, energy of reaction decrease after formation of product, because of bond making mean energy decreasing here. after formation of product. That's why your product energy is less than reactant. Now the difference is called, the difference is called, you know, the difference, you know, change in energy, change in enthalpy delta H is equal to, you know, HP minus HR according to thermodynamics. Here reactant value is more, reactant energy is more than product energy. Therefore here HR greater than HP. Therefore delta H is equal to negative value coming. That's why this graph indicates, this graph indicates what? It is a exothermic reaction, exothermic reaction graph. Exothermic reaction. Here EAF value indicates what? Activation energy for forward reaction, activation energy for forward reaction. This is what? Activation energy for backward reaction. Now this one I am taking now. This is what? Activation energy. Now here also one line I am drawing here. This is indicates what? EA. EA what? Backward. EA backward. Activation energy forward. Activation energy is backward. Here EAF indicates what? Activation energy, activation energy, energy for forward reaction, forward reaction. EA what? B value indicates activation energy, activation energy for backward, for backward reaction. Here also delta H is equal to, here also delta H is equal to EAF, EAF minus EA what? Backward, but EA backward is more, EA backward activation energy more than what here reactant forward back activation energy. So here EAB value is greater than EAF value. Therefore finally delta H value becomes 2 negative. That's why it is indicates what? Exothermic reaction graph. It is indicates exothermic reaction. Once again I am explaining. See, now I am making one graph. It is indicates what? Energy versus what? Reaction progress. Now, for exothermic reaction, reactant energy is more than product. Each reactant molecule must possess some energy, that is ET energy. Now whenever it crossing what? ET energy, this is excited state. In excited state, transition state will be forming. Transition state is very highly unstable. It is called transition state. It is very what? Highly unstable, unstable. That's why it is easily converted to product. That's why A plus B having some what ET energy. How ET energy having? Now I am applying some energy. That energy is called activation energy. Some activation energy giving to reactant molecule crossing energy barrier to convert it to product. Here EAF value indicates what? Activation energy of forward reaction. EAB value indicates what? Activation energy of backward reaction. This difference indicate what? Change in enthalpy. Change in enthalpy formula I am writing. Change in enthalpy delta H is equal, delta H is equal to what? Activation energy of backward minus activation energy of reactant, forward. This value you have to remember is a very important. Sometime what delta H value giving now? Activation energy of forward reaction giving in question, asking what is the activation energy of backward reaction. You have to remember this graph for only for exothermic reaction. Now I am discussing what? For endothermic reaction. Same as it is coming for endothermic reaction, but product energy more coming, reactant energy but less coming. That is indicates what? For endothermic reaction. For endothermic reaction graph we will discuss. The reactant molecule must having what here energy barrier, that is ET energy, and proper orientation. Then they converted into product according to collision theory. The reactant molecule the reactant molecule must have energy barrier or ET I am writing, are having more than activation energy, or having more than activation energy, more than activation energy. Or second condition, having what? Proper orientation, proper orientation. Reactant molecule must have more than activation energy or proper orientation to convert it to product, to convert to product, to convert to product. Already this one I explained already. Reactant molecule must have some energy, it converted to product, that energy is called threshold energy given. Now what are proper orientation? Remember, proper orientation of reactant molecule leads to the what formation of product. Improper orientation of reactant molecule not leads to the what formation of product. Now what I am writing here, proper orientation, proper orientation of reactant molecule, reactant molecule, proper orientation of reactant molecules leads to formation of product, formation of product. Remember, proper orientation of reactant molecules leads to the formation of product, but improper orientation, improper orientation of reactant molecule, reactant molecules do not leads to formation of product. Improper orientation of reactant molecule do not lead the formation of product. For example, I am taking what? Methyl iodide taking now. Methyl iodide. Methyl iodide react with OH minus ion. Now in methyl iodide, iodine carries partially negative charge. It is a nucleophile having what partially what negative charge. So this is improper orientation because of I minus directly combined with OH minus here due to repulsion. They are not directly replacing here because of due to repulsion. This is improper orientation. We are already computed what it in SN2 reaction. In SN2 reaction, the reactant molecule must have what proper orientation, but here improper orientation is there. Directly I am front side, I am nucleophile not attacking because of due to repulsion what product formation is not taking place, no product, that is why it is called improper orientation, improper orientation. improper orientation of reactant molecule do not lead the formation of product. Definitely for formation of product, reactant molecule must have what? Proper orientation. That's why now nucleophile attacking what in a backside in SN2 reaction. You know what better here, in SN2 reaction we are already computed like this. In SN2 reaction, methyl iodide taken now, the nucleophile OH minus is attacking what in a backside. At the same time what I minus easily what here breaking. Finally first to form transition state we are already computed where in organic chemistry what SN2 reaction. Now OH delta minus here what I delta minus first to form transition state. First OH minus attacking in backside first to form what transition state. Here partially bond is making and at the same time partially bond is breaking. It is a slow step, you already computed in organic chemistry, slow step and RDS, rate determination step, RDS step. Now finally, now this transition state it is a very what unstable, it is a unstable, easily converted to product. This is a fast step easily converted to product, loss of I minus ion easily taking place to form methyl alcohol. This is what proper orientation. This is called what here? Proper orientation. Proper orientation of reactant molecule leads to the formation of product. Improper orientation of reactant molecule do not lead the formation of product. This is explained by what? Collision theory. According to collision theory already explained now, each reactant molecule must have minimum energy converted to product. That energy is called threshold energy. The energy giving to reactant molecule converted to ET energy, converted to product, that energy is called activation energy. Activation energy I discussed here. Now activation energy I am find outing for exothermic reaction and endothermic reaction given now. For exothermic reaction what? EA backward, EA forward minus EA backward. Value given EA forward minus EA backward reaction always is negative value is coming now. Remember students. Next I am going to discussing here collision frequency. Collision frequency is nothing but the number of collision taking place per unit volume or per unit time. Per unit volume in per unit time, it is called collision frequency. Actually collision frequency, number of collisions increases, collision what of reactant molecule increases, collide to each other reactant molecule converted to products. The number of collision increase, rate of the reaction also increase. The number of fraction of molecule which are having more than activation energy, the number of fraction of molecule increase, rate of the reaction also increase. Finally, rate of the reaction depend on number of collision molecule and number of fraction of molecule. So that's why what I am writing here, rate of reaction depend on, rate of reaction depends on collision frequency and what? Fraction of molecule, e to the power of minus EA by RT. Therefore fraction of molecule increases what? Rate of reaction also increase, number of collision increase, rate of the reaction also increases. So this is what collision frequency given in collision theory. Next class we will continue now in chemical kinetics chapter. First problem I am going to discussing. Show that the rate of reaction becomes to double when temperature increasing by 10 degrees Celsius given here. Activation energy given 54 kilojoule per mole given. Asking show that what rate of reaction almost double when temperature increase every 10 degrees Celsius given. For suppose now temperature T1 300 300 Kelvin taken now. Temperature increasing what? 10 degrees or 10 Kelvin temperature increasing. 310 Kelvin temperature taking now. Now asking show that what rate of the reaction what double I am telling when increasing in the temperature every 10 Kelvin temperature. According to what here what Arrhenius equation at two different temperature already equation given. Law K2 by K1. You know law K2 by K1. Law K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Now EA value is given here, activation energy EA is equal to 54 kilojoules. Kilo is nothing but 10 to power of 3. Kilo is nothing but 10 to power of 3 joule per mole, and R value you know in joules 8.314 joule per mole per Kelvin. Here T1 temperature 300 given, 300 Kelvin. T2 value 310 Kelvin temperature given. Remember my dear students. Now all given value substituting in this equation. All given value substituting in this equation. Finally we will get finally we will get log K2 by K1 value. Whenever I am solving what this what part, finally we will get value 0.30. Log 2 value 0.30 value you know log K2 by K1 equal to this is log 2 value. In both side log will get cancelled. Therefore K2 by K1 is equal to 2. Therefore, K2 is equal to 2 K1. Mean every 10 degrees Celsius the rate of the reaction is double. That's why K2 is equal to 2 K1. Write out this one. Next problem I am going to discussing now. Now next concept I am going to discussing determination of order of reaction. Methods to determine order of reaction. Method to determine order of reaction. Methods to determine order of reaction. First method I am going to discussing half-life method. Half-life method already given. For nth order reaction, T of is inversely proportional to what initial concentration power n minus 1. A is nothing but initial concentration, that equal to C naught also taken now. A is nothing but initial concentration of reactant at T is equal to 0 time. Now this equation I am applying for two condition, two states. Now T of 1 divided by T of 2 taking now. T of 1 divided by T of 2 equal to A2 by A1. A2 by A1 power n minus 1 coming. Here n is nothing but order of reaction. By using this formula, we can also find out in what n value. N is nothing but order of reaction. Here n is nothing but what? Order of reaction. N equal to order of reaction. N is nothing but order of reaction. N is nothing but order of reaction. N value also find out in. Now I am taking logarithm in both sides. Now I am taking log on both sides. Log base 10 value taking in both sides. Finally we will get log T of 1. Log T of 1 divided by what? T of 2. T of 2 equal to n minus 1 into log what? A2 by A1. A2 by A1. A1 is nothing but initial concentration of the reactant. A2 is nothing but final concentration of the reactant. I am going to find out in n value here. N minus 1 equal to log T of 1 divided by T of 2 divided by what? Log A2 by A1. Therefore, finally n is nothing but order of reaction. N is equal to 1 plus log T of 1 by T of 2 divided by log A2 by A1. By using this formula, we can calculate the what? Order of reaction by using what? Half-life method. The n is nothing but here order of reaction. Order of reaction. Order of reaction. So this is called what? Half-life methods. Half-life method, n is equal to 1 plus log T of 1 divided by T of 2 divided by log A2 by A1. See, after understanding what half-life methods, let us discuss about what want of differential method. Want of method. See, by using want of factor method also, we will find out the order of reaction. Order of reaction. For nth order reaction, for nth order reaction, minus dC by dt is equal to k into C to the power of n. See, according to want of method, for nth order reaction, the decomposition of hydrocarbons follows the equation given k is equal to 4.5 into 10 to the power of 11 second inverse into e to the power of minus 2000 28,000 given divided by T in Kelvin, asking what? Calculate the activation energy. This equation I am comparing with the Arrhenius equation. You know Arrhenius equation, k is equal to A into e to the power of minus EA by RT. Now these two equation, now comparing equation number 1, this is equation number 2. Here e to the power of minus EA by RT value, this value given here, e to the power of what? This equation I am comparing with e to the power of minus EA by RT equal to what? E to the power of minus 28,000 Kelvin divided by T given here. Therefore, EA by minus EA by RT equal to what? Minus 28,000 in Kelvin divided by T. Now TT will get cancelled, in both sides negative negative will cancel. Now EA is equal to EA by R. EA by R equal to 28,000. 28,000. I am asking what activation energy. Therefore, activation energy EA is equal to 28,000 into R. R value I am taking what in joule, 28,000 into R value what 8.314 joule per mole per Kelvin. Finally, activation energy EA is equal to answer coming 232 point, later you do 232.7 kilojoule per mole. Final answer I am writing in kilojoule per mole. Once again listen here. Now first given equation I am comparing with a Arrhenius equation, K is equal to A into e to the power of minus EA by RT. Now this equation I am comparing, therefore minus EA by RT is equal to minus 28,000 divided by T. In both sides TT will get cancelled. Therefore EA by R is equal to 28,000 coming. Activation energy EA is equal to 28,000 into R. R value universal gas constant I am substituting 8.314. Finally we will get EA is equal to in kilojoule 232.7 kilojoule per mole. This is final answer. Next class we will continue from here onwards. This is what chemical kinetic chapter, almost I discussed what last concept I discussed what collision theory. Collision is a very important, and rate constant of first order reaction in terms of gaseous phase reaction also I discussed. Now based on these formulas you will solve all problems in according to NCERT. Next class we will continue one more chapter. Thank you my dear students.